Hi, I'm Ningqiang Song, a postdoc at Queen's University and Perimeter. I will talk about the constraints on WIMPy in elastic dark matter in light of recent low background experiments. This is based on my work with Ben Brauman, Serge Nagoni, and Aaron Vincent. Evidence shows that dark matter must exist in our universe. This includes the bullet cluster and their gravitational lensing, the CMB isotropy, and the galactic rotation curve. In particular, we can establish the circular velocity of the stars by imaging the motion of these stars near and far away from us. And these are represented by these black dots and their asymptotes. If we only consider stellar components in our analysis, which is represented by this gray line, we see it deviates from the observations. But if we include the dark matter halo, which is represented by this orange line, then in combination, the theoretical prediction can be well matched to the observations. From this, we also know that the dark matter is visualized in Milky Way. And locally, dark matter has some Maxwellian velocity distribution with the velocity at about 0.1% the speed of the light. And the local escape velocity is about 500 to 600 kilometers per second. But in the absence of solid evidences of direct detection dark matter events, we still don't know the dark matter mass as well as how they interact with the standard model particles. One type of dark matter that is well motivated is called WIMP, or weakly interacting massive particles. They are predicted by many supersymmetric theories. And in this model, dark matter has mass in GeV to TeV range. And in the early universe, they were in thermal equilibrium with the standard model plasma. But when the plasma temperature drops below the mass of the dark matter, they began to freeze out. The miracle is that we can predict the correct relic dark matter abundance with some weak scale thermal freeze out cross section. And if we look at the WIMP and the standard model matter scattering cross section, it is about 10 to the minus 39 centimeter squared. We can compare this with the constraints from recent xenon, argon, and low threshold cryogenic experiments. We can see that this cross section is almost excluded in GeV to TeV mass range. This raises the question of whether WIMPs are dead or they are dying, and indeed, there are some articles claiming that. But we want to argue that WIMP dark matter are still alive. In 2014 and 2015, Bermanti and his collaborators has studied the parameter space of neutralino dark matter that still survives from direct detection experiments because of the mass splitting between dark matter states. And here, I would like to introduce a general type of inelastic dark matter. In the Lagrangian, we can often find some off-diagonal mass term, and if we diagonalize the mass matrix, we find two mass eigenstates. And if the off-diagonal element is much smaller than the diagonal element, the mass splitting will be much smaller than the mass of the dark matter itself. One application of such kind of dark matter model is the dark photon mediated exothermic dark matter model that we have adopted to explain the xenon one-time excess. In this model, the off-diagonal mass term comes from spontaneous symmetry breaking. Inelastic dark matter may interact with the standard model in two ways. One is the tree level upscattering, while the lower mass state is upscattered to the heavier state. Another is elastic scattering. But this kind of interaction is suppressed by the loop, so the scattering cross-section could be very small. So we focus on the former scenario. Let's look at the kinematics. Because of this mass splitting, from energy conservation, we can derive the minimum and the maximum momentum transfer in this kind of scattering. We require the square root to be positive, which imposes a minimum velocity, which is related to the dark matter mass splitting and the reduced mass between dark matter and the nucleus. This is to say, the dark matter particle must obtain some minimum velocity in order to jump over the ravine made by the mass splitting. To see why they can escape the search and direct detection experiments, we can look at xenon 1 Beyond this dashed line, the dark matter velocity has to be larger than the escape velocity in order for the scattering to happen. So this is kinematically forbidden. But this does not mean xenon 1 is sensitive to the mass splitting up to 430 keV. You can see from this figure that this region enclosed by the green line is the allowed recoil energy of xenon atom in this kind of scattering. And the xenon 1 has only analyzed the nuclear recoil energy up to 400 kV, up to 40 kV. And because of this, xenon 1 can only exclude the parameter space for the mass splitting up to 240 kV. We can also look at the crest. So we can see beyond this dashed line, the minimum velocity is again larger than the escape velocity. But now this corresponds to the mass splitting of about 600 keV. This is larger than xenon 1 because the target has tungsten, which is heavier than xenon. But also because xenon 1 is only, because crest is only sensitive to the nuclear recoil energy of up to 120 keV. So it will be able to exclude the parameter space for the mass splitting up to 430 keV. These two examples motivate us to think about two criteria in setting bound on inelastic dark matter. The first is that the target nuclei must be heavy enough to maximize this reduced mass. In the ideal case, we want the target nuclei to contain 200 nucleons or even more. And lead is such an example. The other criterion is that the experiment must be sensitive to high energy deposition, up to MeV or even higher. The second criterion could be hard to achieve because in the high energy deposition range, we may suffer from high background. So instead, we propose to look at nuclear excitation. In this kind of scattering, the lighter mass state of dark matter is scattered into the heavier state. At the same time, the nucleus is excited to some metastable state, and then the excited nucleus will decay to the ground state by the emission of a gamma quantum. The kinematics is very similar to the nuclear recoil case, but the mass splitting is replaced by itself plus the excitation energy. We can also compare these two types of interactions. For nuclear recoil, the signal is the recoil energy, which can be measured by some scintillating bolometer. And there, the detector itself is the source of the signal because dark matter will interact inside the crystal. For nuclear excitation, we detect the de-excitation gamma, and there, the dark matter will interact in the target metal and produce gamma ray. The gamma ray will be picked up by some external gamma detector. The scattering for nuclear recoil is coherent, which enjoys the A-squared enhancement factor, and the nuclear form factor is the Helm form factor that we see every day. In terms of kinematics, the scattering is penalized by the mass splitting of the dark matter. But for nuclear excitation, the scattering is incoherent because dark matter only interacts with the surface nucleons. When we calculate the form factor, we have to consider the nuclear transition. And in terms of kinematics, we have to overcome both the mass splitting and the excitation energy. Now I will introduce these two different experimental techniques. Let's look at the scintillating bolometer first. In a scintillating crystal, a particle may strike the crystal and produce some scintillation light. At the same time, they will deposit heat in the crystal, which will be picked up by the bolometer. As you see from the figure below, the change in the temperature is proportional to the energy deposited in the heat channel. Because of this, we have two kinds of readouts when a particle strikes the detector, which is the heat channel and the light channel. And if we plot the events, we can find that they can be grouped into different types of interactions depending on their light to heat ratio. For electron and gamma events, they have relatively high light to heat ratio. And for alpha events, the ratio is relatively low. And the nuclear recoils have even lower light to heat ratio, so that they lie in different bands. The experiment we have used in our analysis has used the calcium tungsten oxygen scintillating bolometer, and the accumulated events are shown in this figure. And we can see clearly the electron and gamma band, the alpha band, and the nuclear recoil band. And here we just assume that any events that have led to heat ratio smaller than the alpha particles are dark matter candidates. And similarly, we have also looked at lead tungsten oxygen crystals, and the accumulated events are also shown in this figure. Similarly, we assume all the events with smaller light to heat ratio than alpha events are dark matter candidates. And we found 7 such events in lead tungsten oxygen experiment. Well, we have also looked at nuclear excitation search. In particular, we have collected the gamma spectrum of hafnium samples, which is picked up by gamma detector, and the hafnium sample is shielded by lead and copper. And here is a zoom in of our signal region. To set bound on dark matter, we require that the dark matter induced excitation rates not to exceed the gamma signals that we have collected. Another experiment for nuclear excitation is the gamma search of osmium. And in this figure, we show the accumulated gamma spectrum of these osmium samples. And we have used the lower energy part of the spectrum to set bound on dark matter induced excitations. All these experiments were carried out in Grand Sasso, which will shield the detector against the cosmic rays, but dark matter can still scatter in the detector and produce some signal that we can analyze. Prior to our work, inelastic dark matter are constrained at low energy, at low mass splitting by Zina Wang and in 200 and 400 kV mass splitting by pico and crest, and in the higher mass splitting by the de-excitation of tantalum atom. Here in this figure, we show our results for nuclear excitation. And on the left, you can see the spectrum of the osmium gamma surge, and we require the induced nuclear excitation not to exceed this spectrum. And we have produced the results from hafnium and osmium transitions. In particular, the osmium 36.2 keV transition has allowed us to put constraint on the dark matter mass splitting on dark matter interaction cross-section up to the mass splitting of 540 keV for the dark matter mass of 1 TeV. And we have also analyzed the results for nuclear recoil because we can distinguish different event types based on the light to heat ratio. And from the results of calcium tungsten oxygen crystal and the lead tungsten oxygen crystal, we can constrain the cross-section for the dark matter mass splitting up to 640 kV. Here we also assume the mass splitting of Here we also assume the dark matter mass of 1 TeV. At high mass splitting, this is mainly constrained by PBW4 scintillating bolometer. So you may wonder how the constraint look like for different dark matter mass. And for that, we extended the dark matter mass to GeV. And in this figure, you can see the minimum cross-section bond for a specific mass splitting and the dark matter mass. Similar to the previous figure, we can see at low mass splitting, the cross-section are mainly constrained by xenon 1 and in 200 to 400 kV mass splitting by crest, and higher mass splitting by CW4 and in the tail by PBW4 scintillating crystal. Another limitation factor when we explore the parameter space for large mass splitting is the velocity of the dark matter. In many scenarios, dark matter can be boosted to high velocity. For example, they can be boosted by the scattering with cosmic ray or high energy cosmic neutrinos. They can also be boosted in the stellar objects like the Sun, or they may be produced from annihilation, semi-annihilation, or heavy dark matter decay. Regardless of the boost mechanism, we just want to show the kinematic range of this boosted dark matter. So we assume a dark matter maximum velocity of 1,000 and 2,000 km per second, and we plot the parameter space that we can cover with these maximum velocities. We found that if we assume 2,000 km per second of maximum dark matter velocity, a lot of the parameter space for the mass splitting below MEV can be covered. We just kept it at 1 MEV because in many models, if the mass splitting is heavier than 1 MeV, they will decay quickly into electron and positron, so that the heavier state will decay and produce different phenomena in the detector, and we haven't considered that scenario in our analysis. In the last slide, I show some brief conclusions. I have showed that WIMPy dark matter are still alive, in particular if we consider inelastic dark matter. And we have searched for this dark matter with the nuclear recoil in CW4 and PBW4 scintillating crystal scintillating bolometer experiment. And we have also searched for them when they induce transitions in hafnium and osmium samples. In the future, we can possibly do some model-dependent analysis to see what kind of constraint we can put if we assume dark matter are boosted from some mechanism and how we extend the reach of the mass splitting. Thanks.